Hello and welcome to the talk on the OpenPOWER Summits 2021. Thank you for the opportunity to give this talk. It's going to be about draft SVP64, which is an extension to the power instruction set to provide Cray-style vectorization, and we're going to specifically cover in-place matrix multiply and fast Fourier transform, discrete cosine transform, and the possibility of doing number theory NTT transform within the power ICE instruction set. So just a brief thing about the overview of the Libre-SOC goals here, which this is part of the Libre-SOC project. It's sponsored by both NLNet grants and NGI Pointer grants. But it's important to understand what our goals are here so that you understand why it is that we're driving towards these particular optimizations. A primary goal is to create power efficient mass volume products that are simple to program for the users by the developers. We want to leverage the amazing OpenPOWER ecosystem to do so because of its pedigree. It's a supercomputing class instruction set already, and there is over 20 years of software. We need to be entirely transparent for security reasons, which are important for when it comes to businesses, because we want to empower businesses to bring secure, transparent mass volume products to market. You will have seen the mess with Qualcomm. 40% of Android smartphones were discovered to be insecure. You will have known about the Intel Management Engine and Huawei and Supermicro. So we need to develop mass volume end user products, and obviously those need primary focus for those is 3D video and audio codecs, and therefore, as far as 3D is concerned, we require small size matrices, 3x3 and 4x4, and the core strategic parts of audio video codecs, which I was really surprised to find out, means discrete cosine transform and FFT. I was stunned. The Wikipedia page lists like 70 to 120 different applications for discrete cosine transform in different areas of computer science to do with audio, video, and digital signal processing. It's pretty important algorithm. Anything else that we can get on top of that is a bonus. Now, it turns out that a number theory transform, NTT, is basically discrete Fourier transform, but using Galois field arithmetic. And that turns out to be extremely important in Reed-Solomon. It's the core fundamental basis of it, and optimized algorithms using NTT rather than the standard method are extremely efficient. The reason I mentioned that 3x3 is particularly important is because if you have a power of 2 SIMD backend engine that requires to have operations of length 4, then the only way to do 3x3 matrices is to run at 75% utilization. And if you do that with and you're attempting to enter into the current commercial 3D GPU market, right off the bat, you're completely hosed. It's a waste of time. So we have to be able to do full 100% utilization of the back-end in infrastructure, and that means because of the 3D GPUs, they have X, Y, and Z matrix multiplies. It's absolutely essential to have these arbitrary size, non-power of 2 matrix multiply support. So we're looking for high performance and high performance per watt. We're looking primarily for efficiency here. This can be done in terms of reducing the code density, which turns into reduction in iCache usage. If your hot loop is a few instructions that are repeated, then it saves a massive amount of power. And there's a paper on by Etheric group which showed that when you have these auto looping systems combined with sys-like load and store to run on a single instruction, you can get up to a 3.5 times power consumption reduction and energy efficiency, which is pretty stunning for something that, I mean, the core, it's pseudo dual issue. It's not even multi-issue. It's not out of order or anything. It's a pretty amazing achievement. The algorithm's complete in like between 2 and 6 times less actual instructions executed. We want to remain accessible for both assembler writers and compilers alike. Nothing too esoteric, shall we say. I have done programming of esoteric things at the rate of 1 instruction every 5 days. It is it was truly awful and just wasn't worth the time. We also want to introduce true vectorization to the power instruction set. VSX is packed SIMD on power of 2 binaries boundaries only, and it's showing its teeth, unfortunately, showing its age. An also important goal is to be adopted via the external OpenPOWER Foundation ISA work group RFC process. I specifically mentioned the external adoption process there, not the internal members work group one. And it's also critically important that it not be a non-official kind of custom extension. Although the option exists to do that in the end user license agreement for the Power ISA, it will be very risky for the stability of the OpenPOWER ecosystem if SVP64 was not adopted. And the reason is because the proprietary custom extensions are expected to be small, private, hard forks of the ecosystem, hard forks of the compilers, hard forks of the libraries, whereas we are targeting mass volume adoption. That means that if we are forced to go the custom extension route, we end up with 100,000 developers hammering our website for GCC, libc6, etc., and they will swamp and overwhelm the upstream resources demanding adoption of these modifications. Consequently, we need help to ensure that what we go ahead with commercially is actually stable and usable and useful and stands a chance of adoption. We need help in going through the ISA workgroup RFC process. It cannot be left down to us. So here is a reminder of what Simple-V is. I've provided the overview link, and hopefully you, as you're listening, to from the abstract, you understand what it's Simple-V is about. But in a nutshell, it is greatly simplified. It's this: for each instruction, up from I equals 0 to vector length minus 1. You perform the same operation, the same scalar operation, repeated, incrementing along to the next register. And when you get to vector length VL at minus 1, you stop, you reset the loop, and you then and only then do you move to the next instruction. And it's very similar to the x86 rep instruction, except that you increment the register numbers as you go along. A little bit more involved version is that each of the registers RT, RA, and RB can be marked as vectorized or scalar. And in addition to that, we have predication. And this is all tagged registers. It's register tagging in a prefix that fits into SVP, into the 64-bit prefix system, where we're overloading the Power ISA v3.1 prefixes. So Let's have a quick look at the difference between what happens with remap. A remap system, right? The basic core is this operator here, where in this one you've just GPR RT plus ID, where it was just incremented by 1. That number incremented by 1 goes through a hardware finite state machine remap function. And there are actually 4 of those, because you can have multiply and accumulate things. So there's one remap for remap for each of the 4 arguments of multiply and accumulate. So let's jump into the basics of matrix multiply. Basically, you do each of these. This row times that column goes into this value here. Then this row times that column goes into there, and likewise for those. So you end up with these C00 is this sum here, C01 is this sum here, and likewise for the thing. Now notice that I deliberately put this, swap these round, and you get, in this case, you get a 2x2 result, and in this case, you get a 3x3 result. It's quite deliberate to show you that. So a naive version of this with Python for loops, you have 3 nested for loops. The outer one here, this one here, and then this one here, and you basically perform a multiply and accumulate to create the product. And you get the general idea. Now, the problem is that multiply and accumulate is completely unsuitable for hardware scheduling. Right? It will create massive read after write dependency headers in your execution engine. All you need to do is to swap these 2 loops. You do not change this at all. It's exactly the same thing, but all you've done is you've swapped these two loops, and what that results is it begins to accumulate, partially accumulate results in the J index, but of course that's moving on. IJ, there we go. And what's nice is that this one stays in the register, whilst this one moves on. But you can overlap by doing this trick. You can overlap multiple of these multiply accumulates in a targeting different registers. Where this one you can see, because it's product IJ, I and J remain the same on this inner loop. Yeah? So simply by moving that to there, this one changes, and you end up in the back end targeting different registers. So this gets interesting with the moment. If you're going to do that, swap those loops, well, why not make it general purpose and make a general purpose nested loop system? So this means that you have other uses. You can have other algorithms beyond matrix multiplication. We can do arbitrary size loops. We can do any permutation of nesting, and we can also specify reversing per dimension, which, very interestingly, when you apply that to matrices, what it means is that you do not have to do transpose copying of the matrix in order to multiply them. Right? If you want to do a rotation of a matrix, you don't bother to actually do a copy of that matrix. You just set a different permutation of a nesting, and you reverse one of the dimensions, and you've inherently in place transposed, but as you use it as one of the input operands, you've inherently in place transposed it. So we've got the generalization, but also we want to specialize to make it very easy to set up a matrix multiply. So we want it to be quick and easy. So we have two 32-bit instructions set up the A, B, and C sizes, which is you only need 3 dimensions here. You need that one, that one, that one, and I think it's that one to give you enough information to create this the thing. All right, and then there's one 64-bit SVP FMAC instruction, which is your hot loop, and nothing else is needed. 3 instructions. It turns out the hardware is near identical to zero overhead loop control, which was researched. There's a research paper on that in 2006 and some source code about it. I provide a link there to the REMAP system there. But fascinatingly, the concept of this general nested loop system, I actually borrowed it from the Aspects Microelectronics ASP, which had a 1D, 2D, 3D arbitrary memory DMA reordering engine with read and write capability, where you could specify any jumping to up to 3 dimensions of depth to load data from memory and put it into the 1D massive wide SIMD processor. But the difference here is that it applied it to the register file instead of to memory, and more on that later, because actually it might actually be a good idea to actually do it as memory. So these are the 3 instructions. You set the shape, and that's your A, B, and C. So what we're saying here is only by having these 3 pieces of information can you determine the sizes of the A input, B input, and C output. So that 3 is there and there and there and there. That 4 is there, and that 5 is there. So that determines that those 3 numbers determine the shape of both your A and your B and your C output. The remap instruction there says I want you to remap this shape onto this shape is register A, that's register that's RT, that's RA, that's RB, and you get the idea. So there's 5 possible registers that you can target, and you want to say which one is enabled, which one goes to which, and then you just use the multiply and accumulate. That's it. I'm really not kidding. That's as simple as that. So yeah, that's all, folks. There are no. The whole point of SVP64 is there are no actual vector ops. We do not add vector operations. I will say that again. We do not add any vector instructions. It is entirely done through the x86 rep-like concept of a prefix on top of a scalar instruction. We also do not dictate or limit the microarchitectural detail implementation. Right, that is very specific. There is no restriction or limit or imposition on what you can do and how you can do it. You can do a finite state machine similar to Pico RV32 implementation of SVP64 if you really wanted to, or you can go a full-on massive 8-wide multi-issue architecture, basically using the IBM Power 9 or IBM Power 10 internal hardware, and simply putting SVP64 in between issue and execute phases. So as I said, it issues scalar FMAX into existing backend hardware. We are not limited to just to the FMAC instruction. It can be any 4 operand instruction. We could do Galois field multiply and accumulate. We could do integer multiply and accumulate. We could even do bit manipulation version of multiply and accumulate. As far as SVP64 remap schedule is concerned, it doesn't care. Right? There are also no power out of 2 limits. I will say that again. There are no power of 2 limits. The vector length, these numbers here I very specifically chose to be 5, 4, and 3 to illustrate that it is not power of 2 limited. Again, the way that SVP64 works, because for SVP64 works because the separation, you can have any operand width. You can have 8-bit operands, 16-bit scalar operands, 32 or 64. Right now, one limitation is that we're limited to 127 scalar ops at the back end, and that's down to the limit on the number of on the size of the vector length VL. It's also limited to in-place registers. So if you want 128, if you want very large matrices, you will need 128 wide scalar register file. In the future, we can do things like that paper we discovered, which is by ETH Zurich. The basis of that is that they did a CISC-like load and increment, which is based on auto load and store with tagged registers. So they tag 2 of the floating point registers as being auto load and increment, direct that through to the memory backend, a synchronized memory backend. And the advantage of this is that you do not have to modify the RISC instructions. I say you're doing tagging. It's register tagging, which is a concept introduced by Textron Instruments in the 1980s. In this way, if we add auto load and store, we can extend to memory-based arbitrary n-by-n matrix sizes. There is absolutely no reason why we shouldn't be able to do 10,092 by 750,061 sized matrices. And it would still be power efficient because there would be 0 iCache usage during that FMAC issue, because it's a single instruction hot loop. We put in a very large 2.6 million euro EU grant. We will be looking for collaborators for this. There's enough for 40 full-time staff to work on this SVP64 and the Libre-SOC project for implementing the Power ISA. So we will need some help with that, and these things can be investigated as part of that. So we've got the basics of REMAP, and I want to, how are we doing for time? 23 minutes. I just wanted to go over the REMAP thing. You'll have to look at this yourself online. I will provide URLs later, but here is the basis of the looping. This is a simulation. It uses Python yield. And here's the limits, the A, B, and C limits, which were set in that example to 5, 4, and 3. Here is the order in which you want them to be done. And there's a simple algorithm here to calculate the offset. So it turns that 3D number into a 1D number. But what you can see is this selection. It allows you to do a pause in this for loop. So when you are basically you have 3 remaps, one to produce I, which obviously needs to pause whilst J and V are running, another one for J, which needs to pause whilst V is running, and finally the V one will just go rattle around the around the inner loop. So this is the bit that fascinatingly turned out to be extremely easy to implement, or remarkably similar to zero overhead loop control. Now, can we? The next target, I was really surprised to find, or shocked to say, to find how much power could be saved by reducing the number of instructions for discrete cosine transform just by having straight SVP64 one-dimensional vectors. So then I looked at it and went, can you do a remap schedule, a triple inner loop, just as similar for the matrix multiplies for fast Fourier transforms and discrete cosine transform, etc., etc.? And the answer turns out to be yes. It's a lot more complicated than the matrix schedules, but it's exactly the same principle. So again, you have these a triple loop system, and you can issue scalar instructions into the back-end microarchitecture, where it becomes that back-end microarchitecture's problem to sort out the issue, etc., etc., and to line up those scalar instructions with appropriate SIMD backend or SIMT whatevers. All right. Now, one caveat of this is that it turns out to do in place FFT DCT, you need 5 operand, that's 3 in, 2 out new scalar instructions. Right. If you didn't want to do in place, you wouldn't need them. And again, it's any operand width and any type of operation. Right. The remap schedule does not care what instruction it is put on top of. It could be like Galois field, integer thing, whatever. Now, for various reasons, unlike the Matrox Multiply, I had to limit this first implementation to A, in-place registers, and B, power of 2. So again, in future, we can look at under this large NL EU grant we put in, we can look at the CISC-like auto load and store and increment, which means we'll be able to go to power of 2 to 1024 or 64K FFTs. Wouldn't be limited to what fits into the register file. And again, it would still be power efficient because there would be no instruction cache usage in these inner loops. What other implementations exist that took inspiration for and think? Now, these are DSPs, and they're very specific uses. Things. There's a text administers TMS DSPs 320 thing. Please excuse me. TMS 320 series DSPs. The TI's instrument DSPs can do 14 microops per VLIW instruction, and that includes 0 overhead looping. It's a single loop. And it does odd, even FP32. So 7 of the instructions are used for odd FP32, 7 are for even FP32. It cannot do anything other than FP32, but it's an absolutely brilliant and elegant design. Qualcomm Hexagon DSP again is a VIW, but they can manage an insane 29 RISC-like microops in a single cycle. It is seriously power efficient and effective. Again, it has single inner loop, 0 loop control, but amazingly they have complex number multiplication, multiply and accumulate, which is a definite wow. But it only seems to handle the inner loop of fast Fourier transform. It can't do the triples. So SVP64, by contrast, is not limited to the inner loop. It can handle the entire triple loop of FFT. The setup is extremely short in the number of instructions required to do so. It's not limited, like the hexagon, it's not limited to the type of operation inside the loop. But we did consider that doing complex number operations was a bit too heavy duty for now. So we've done complex number ops in a different way. So basics on discrete cosine transform. If you look at the Lee, the original Lee paper, I think it's from like 1983. The standard DC's discrete cosine transform schedule is really messy. It's impossible for SIMD to do efficiently, and you have to do this ridiculous loop unrolling. And that's down to this thing, these kinds of tricks here, things here in the algorithm. So you cannot do it in place, right? If your data comes in order 0, 1, 2, 3, 4, 5, 6, 7, you can do this in order, and this you can do in place. Sorry. This likewise, as long as you have that 3 and 2 output instruction. If you don't, you can't. You're screwed, and you need double the size of the register file. And then there's the outer butterfly. So that was the inner butterfly, and then there's the outer butterfly. But finally, you end up with the data in the wrong order. You end up with it being in bit reversed order. So element 0 ends up in position 0, but element 1 in binary ends up in position 4 in binary. So it goes 04261537. Whoops. And this was the focus of the one of the focuses of the algorithm that I wrote, was to work out how to solve this. Fast Fourier transform suffers from the same thing, although you can do the in place thing. You can even use a temporary variable if you want, if you're doing scalar things. But if you have that 3 in, 3 out thing, it's only one butterfly thing, whereas in this one you have to have two. You have to have an inner schedule and an outer schedule. But again, unfortunately, the output is in bit reversed order, 04261537. So what's involved in the FFT instruction? This is your 3 input and 2 output. So you have your inputs coming in x0 and x1. You also have the coefficient c. So you perform the same multiply here of x0 by your coefficient, but you subtract it from x1 and you add it to x2. So again, I am not specifying, the point of this is not to specify the efficiency of the 3 in 2 out instruction. It can be 2 cycles, it could be 1 cycle, and if you did Pico RV32, it could be 100 cycles. We don't care. We are not specifying. The job of an ISA is not to specify or place imposition on what the back-end architecture implementation is. So there's an absolutely fantastic implementation online called Project Nayuki of different implementations of FFT and DFT and so on. So here's the task of what we started off with. You've got the coefficients here in this table. Here is that bit reversing of the vector, so it swaps it in advance. So the actual input is swapped 04261537, such that the data, when you have performed the calculation, will end up in the order 0, 1, 2, 3, 4, 5, 6, 7. Remember that because it's critically important. This is your triple loop of your butterfly. You go in the power of 2 on n. You go in steps over the from 0 to on that one, and then you get the in loop which does the this. So it goes that one, that one, that one, that one, and then does that one, and that one, that one. You get the idea. Whoops. So the next thing, so what we're going to do here is we're going to transform this into something that matches how the DFT actually works in SVP64. So the next stage is to replace these scalar instructions here with that twin butterfly 3 in 2 out instruction. So it takes as input the x0 and x1 and the coefficient, and outputs those, and only by doing this do we get the atomic operation needed, because these go into your pipelines, into your ALUs as an atomic operation, and you get the 2 registers out as an atomic operation. So you're using, it's a trick, you're using that as a temporary storage. And once we've done that, what we can do is that J, K, and H, they're HS, these values here, we can write a REMAP triple loop generator which creates those 3 indices. And let me just briefly show you that here. I'm sorry, we're going to, which one is this? It's the FFT yield. So here is a generator system where you give it a parameter FG shape, which will be the special purpose register for the shape, and it depending on the mode, it will either return an index for J an index for j plus the half size, or an index for k for your coefficient. Okay, so you have 3 remaps. This is why you have a remap for one register, remap for another, for a second register, a remap for a third register. All right. So that's really basically it. That you create these offsets for these registers automatically with a hardware finite state machine, which is pre-configured in exactly the same way as the Matrox remap system, but done for for FFT, DFT. Right? We only need one actual inner loop instruction in the hot loop, and that's for DFT and for NTT. Now, here's the bit about if we had a complex number multiply and accumulate, it would only be one actual instruction for a full complex number fast Fourier transform as well. We need that thing. So I think I've gone over that for in place FFT because it's 3 out, and just like with zero overhead loop control, it's a hardware finite state machine which creates the offset triplet, and it's technically not that hard to implement. SOTO voice for Radix 2, and again it uses the exact same principle as triple loops for matrices. So turns out that there's a very elegant trick where I managed to work out how to put the data so that it ends up in place. I'm terribly sorry, I'm running out of time to describe it. You'll have to take a look at it yourself in the code. Let's say, yeah, FF remap FFT one. Again, FFT discrete cosine transform yield. Basically what this does, let me see if I can find the thing here. Okay, so after about 6 weeks of messing about, what I discovered was that we can do a double redirection. The first redirection deals with the fact that the input data has to be ordered in that byte reversed order 0436.257. But the second part deals with this byte reversing order of the thing. So unlike with the first Fourier transform, it's like this, where it's even jumping. In DCT, it's like that. But it turns out that we can actually compensate for that with this half swapping system. It's double in direction, and there is an extremely elegant mathematical algorithm for calculating that, which simply requires that you take the index number, shift it down by 1, and exclusive OR it over the top, and that calculates beautifully simple and easy to implement in hardware algorithm. You can just is obviously extremely simple to implement in hardware. FFT, you have I apologize for really running out of time as usual. It's an incredibly short amount of time to do this such a complex topic. Everything is online, by the way. For discrete cosine transform, the problem is that one of the problems is that the coefficients change because it's a cosine plus 0.5 depending on the layer, so it can't be done as a single instruction, and we've worked out some workarounds for that. For FFT, complex number butterfly multiplies actually involve 4 multiplies and about 4 adds or something mad. So you cannot do in place of single instruction. The solution was to add vertical first vectors, which I first saw in Mitch Alsop's VVM extension for his MyISA 66,000 instruction set. You can find him on comp.arch and ask him for access to the ISA documents on that. To understand SVP64 vertical first, I've got a 30-minute video which does a walkthrough on it. It's on YouTube. Basically involves stepping vertically through instructions, then calling an SV step instruction to move to the next remap offset, and then looping back with a branch conditional. But horizontal first goes through the entire schedule on a single instruction, then repeating goes on to the next instruction. So if I can illustrate that, horizontal goes, if you've got your instructions down here, horizontal goes 0, 1, 2, 3, 4, then moves on to the next instructions as 0, 1, 2, 3, 4 for 0 to vector length, whereas vertical first does everything in with index remap index equal to 0, then goes on, loops back and goes on to do 1 and then 2 and 3 and 4. So yeah. So summary here. Our goal is to create a mass volume, low power embedded SoC suitable for use in networks, Chromebooks, tablets, smartphones, IoT, single board computers. This means a computational focus on 3D audio and video. And again, we note and reminder that it's critical for commercial success of such a product not to waste 75% of power to SIMD lanes on 3x3 matrices, to the point where ARM actually put special instructions into Mali to deal with that. We're reducing the core work down to a one instruction hot loop, which inherently reduces power consumption because the instruction cache is 100% idle. Remap system is completely independent from the instructions it is remapping on, and consequently that applies to future scalar ops. So for a power ISA 3.2, if you've added any 4 operand scalar instruction, remap will apply to it automatically, inherently, without requiring the addition of explicit vector operations. This is one key difference of SVP64 prefixing. Right. Future versions we can do that IEEE trick to do proper zero overload loop control and put hidden tags, and that will allow us to span out to massive data sets way beyond what can fit into a register file, which is the target of a GPU. That's its primary goal thing, but we can extend beyond that to supercomputing workloads. So please help contribute to this. It's your OpenPOWER ISA as well. Please don't leave it up to us to submit this to the ISA working group as RFCs. We need your help in reviewing this work to make sure that it is stable for long-term use for the next 20 to 30 years. Thank you very much.